Hi there, I'm Matthew and I'm here with Pico technology on the stand here at ARMS 2023. At ARMS we've just released the new version of the PicoVNA 5 software. This is version 5.2.6, and with 5.2.6 we've brought loads of new features to do with remote control of the PicoVNA instrument, and we've added a lot of new API functionality. So in this video I want to deep dive into some of that functionality. We've just recorded a separate video on remote controlling the PicoVNA 5 software via Skippy. That's not what I'm going to be doing in this video, so we're not going to be doing much in the PicoVNA 5 software itself. Instead, I'm going to be controlling the instrument directly via our powerful programming API. Now, you can obtain our programming API from our software development kit, which is downloadable on the Pico technology website. Within the software development kit, we have a lot of programming language bindings. We have bindings for Python, MATLAB, C++, and we're constantly growing the number of languages that we have bindings available for as we're growing our really active community of users around the SDK and API. All of the code that I write in this video is going to be available from the downloadable SDK. So the setup that I have here on the stand is I have a PicoVNA instrument that's just off camera, but that PicoVNA instrument is connected to the Pico Technology Network Metrology board. And here the PicoVNA instrument is just measuring the bandpass filter that's available on the board. So if I switch over to the PicoVNA 5 software briefly, you can see that we're measuring this bandpass filter, and we've got 6 dB points at about 161 megahertz and about 220 megahertz. But as I said, what I want to do in this video is demonstrate the low-level API control of this instrument. So let's go ahead and close the PicoVNA 5 software and instead open Python. So what I've done is downloaded the SDK and copied over the libraries that I need out of the SDK. There are instructions for doing all this within the SDK documentation, and I've also installed the VNA package from PyPy. So using pip3, I've installed the VNA package. So let's just import that. Let's start off by connecting to the instrument. So let's open that. There we go. It's the correct version. And let's just verify that I've connected the correct instrument by printing out the serial of the instrument. So there we go. I've printed out that I've got the instrument with serial 09464 connected, and that is indeed the serial of the instrument that's connected to my laptop via USB. So let's go ahead and set up a simple measurement. What I'm going to do is create a measurement configuration. I'm going to just add a simple uniform frequency sweep, so a linearly spaced frequency sweep to that measurement configuration. Let's make that 1001 points. Let's start at 300 kilohertz and let's stop at 8,500 megahertz. So sweeping over the full range of the device bandwidth there. Let's sweep with 0 dBm power level and 1000 hertz bandwidth, 1K bandwidth. What I'm going to do is just perform those measurements. So let's do that. And the function that I'm using here, perform measurement, is performing those measurements synchronously. So it's going to return the results into a Python list I could have instead performed the measurements asynchronously, in which case the function would have returned immediately. I'd have used the start measurement instead of the perform measurement function to do that, and then I could have processed the measurements point by point as they become available. But this was a fairly fast sweep. So we could run it synchronously and get all the measurements back in this list. So what I'm going to do is just print out some of these. The measurements are all available in a Python list, so let's take the first point and let's just print it out. Let's print out the frequency of that point. And let's just print out the 4S parameters. So there's S11, let's do S21. This is going to print the 4S parameters in real and imaginary format. So let's go ahead and do that. And there we have the measurements in real and imaginary format. But within the Python API, we have a lot of convenience functions as well. So let's say instead of printing these out in real and imaginary format, I wanted to print them out in logmag format. If I want to print those out in dB, I can do that really easily. So let's go ahead and do that for each of our 4 measurements. And there we have our measurements in dB. So that was a simple linearly spaced frequency sweep, but what the API really allows us to do is access the low-level functionality of the instrument. I want to go on to create a different sweep. This is going to be a much smaller sweep. It's just going to be 3 points, but I want to show how I can measure at a different frequency and a different power level for each of those 3 points. I'm going to this time build up the measurement configuration point by point. So let's create our first point, and let's create this at a frequency of 1 gigahertz. Let's measure this with a power level of 0 dBm, so that's what we had before, and let's stick with our 1 kilohertz bandwidth. And let's add that measurement point to the measurement configuration. Let's do this again, but this time use a different frequency. Let's use a frequency of 1200 megahertz, and let's use a different power. So let's give this one a power level of minus 10 dBm. Let's stick with our 1 kilohertz bandwidth as before, and let's add this point to the measurement configuration. And then finally, said we were going to do a 3-point sweep, so let's add one more point. Let's demonstrate that we can add this at any frequency, so something that isn't uniformly spaced from the other 2 points, so put that in at 2 gigahertz. Let's use a power level of, I don't know, plus 10 dBm this time, and let's use the same bandwidth as before. And let's finally add that point to our measurement configuration too. So let's go ahead and perform those measurements. I'll do it synchronously again, so we get the measurements back in a Python list. There we go. It was faster this time because it's only a 3-point sweep. Let's go ahead and print those out, just like we did before. Let's go back to where I had my printing function. There we go, printing these points out in dB. So there's our 1 gigahertz point. Let's take our 1.2 gigahertz point. There we go. We can see we've got a frequency of 1,200 gigahertz, or 1,200 megahertz. And then let's print out our final point here, which had the frequency of 2 gigahertz. So there we go. Hopefully what this video has demonstrated, in part at least, is that the programming API gives us, is really powerful. It gives us this low-level access to the instrument. Here I've been running via Python on my Linux-based laptop. I could have equally well run this code on a Raspberry Pi or other embedded device, or on Windows or macOS. Just like the PicoVNA 5 software, the API is fully cross-platform. As we've said, we can download all of the example code that I've written today, along with many other examples showing the full capability of the API on the Pico technology website. There's full documentation available in our programming guides, one of which is available for each language in which we have bindings. So thanks for watching.